this is where we left off when we were looking at binomial probabilities. We were looking at Devin shooting his free throws, and he has a 90% average. Okay, the example we looked at said, hey, if we're looking at one game and he shoots 7 free throws, and we found some different probabilities there. But let's say we're still looking at Devin. His probability of making a free throw being 0.9. That means his probability of missing is 0.10. And now let's say we're looking at practice one day, and maybe he's going to shoot 200 free throws. And I want to figure out the probability that he's going to make at least 150 of them. Or maybe I want to find the probability that he makes between 175 and 200. Okay. Which is all of them. So maybe we'll say 175 and 185. Or maybe the probability that maybe he's coming down with a cold or the flu, and the probability that he is going to make less than or equal to 50 of them. If we were to go through the steps, then we would be using this formula over and over and over again. We would have 51 times to do this one, and 11 times to do this one, and 51 times to do that one. And that may or may not be a very good use of our time to sit down and compute those things. So there are certain situations that we can make these problems more user-friendly, and we can use what's called the normal approximation to the binomial. So remember our normal distribution from way back when we have already done chapter 6. And our standard normal curve is a bell-shaped curve. The area underneath the curve was 1. It was centered at the mean of our population, which was a z-score of 0. Its standard deviation was 1 in terms of z-scores. And we could use that table E to find areas to the left or to the right or in between two values. Something nice happens with the binomial distribution. If RP is close to 0.5, if RP is close to 0.5, then that means so is RQ. And if N is large enough, and we'll quantify what large enough means here in a minute, then instead of finding the probability that Devin makes 150 and 151 and 152 and 153 and blah 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 and 199 and 200 of these, we can pretend like this is a smooth normal curve, and we can find probabilities using that instead. So read through your book. Your author gives you a good explanation in more detail than I'm going to put here. But before we can go down this path, we have to take n times p, and we have to take n times q, where p is the probability of success, and q is the complement of that, or the probability of failure. And if both of those values are bigger than or equal to 5, then we can use normal approximation to the binomial. So if n is 10 and p, probability of success, is 0.3, okay, that's not a very high probability of success. Maybe the probability of success is 0.8, then that means the probability that we're not going to succeed is 0.2. If we take 10 times 0.8, we get 8, which is fine, that's bigger than 5. But if we take n times q, we only get 2. So we say if we were to draw out this distribution, it would not be normally shaped enough that we could use normal approximation to the binomial. If we check our situation with Devin, where he shoots free throws 90% of the time. Okay, he makes his free throws 90% of the time. Okay, 90% is not close to 50%. It's not in the middle. Okay, but he's repeated the experiment often enough. If we take n times p, we get 180. 180 is most definitely bigger than 5. And if we take n times q, we get 20. 20 is also bigger than 5. So that means we can actually approximate this situation with Devin shooting 200 free throws. We can approximate that using the normal distribution. And we'll talk about how to do that here in just shortly. Probably I'll start a new video on that so these don't get too long today. Okay, so stay tuned for how we're going to approximate the binomial distribution using a normal curve.